How do you actually get the Jacobian easily if you're using DH notation? So we'll make an assumption here at the moment that you have already calculated all of your DH parameters.
Okay.
So we have the table set up and we have all the transforms from 0 to 1, from 0 to 2, from 0 to 3. Notice referenced all the way back. Now if I have all of those, then we have a nice easy way of actually, from those, calculating what is our motions. But we just want to break it into, for our Jacobian, into two pieces. Our Jacobian has partially an area for its changes in X, Y, Z. So I'll call those kind of linear movement parts. These are the changes in X, Y, and Z and how it relates to each of the joints. So if you remember, we have kind of like a theta dot 1, theta dot 2. You might have a prismatic joint in here, in which case you've got some, whatever, D3 dot, however that. So you have a series of variables that's going in. Thetas and Ds, the rotations and the linear movements, and we want to see how those relate, changing to your X, Y, Z coordinates, the linear areas. But in addition to the linear areas, how it's displaced and how fast it's moving in those, you also have a component of how fast it is rotating. So we also have a portion of this that handles angular movement. Alright, so those kind of, and we will have, in essence, kind of rotations that are going on about each of our three axes. So you get a net effect with 6 of these. You get the displacement. So for a rigid body, I get displacements in X and Y and Z and rotations. Right? So omega X, omega Y, omega Z type stuff. Right? So if I know those, I know how that particular body is moving. And in our case, what we're concerned with is the end effector frame. Does that make sense so far? Mm-hmm. Okay. So we're going to actually take advantage of this kind of separation to figure out how to calculate the Jacobian, because this is what we're trying to do. So for any particular one, let's take a linear movement, a prismatic joint for a sec. I want to calculate what that column is. Okay? Now, think about for a sec what's going on here, right? For this one, for the third joint, or it could be in general the ith joint that's going on, I've got some section of robot that connects me up. And we said it's going to be a prismatic joint. So it's got some axis z sub I minus 1, because remember we always label z as one less, so to go from I minus 1 to I, that's the ith joint. Okay? So initially it starts off at I minus 1, at the end it ends up at I. And that accounts for the fact that the first joint goes from 0 to 1. So that was our first joint. So the ith joint goes from I minus 1 to I, so it starts at I minus 1. This one always seems to throw people. With a prismatic joint, I've got the prismatic joint, by convention, is aligned on the z-axis. We could have decided to align it any old way we felt like aligning it, but just by convention, just like we always say that rotational joints rotate about z, we always say that prismatic joints extend along z. That is just part of the DH convention. So that's our kind of situation as it goes on. Now, at the end of this, right, so I have some displacement here that is going to be whatever we call this D3, or in this case, I guess it's DI, right, that ith displacement, and that's a variable, because you can change it. But that's in the z direction. Now, the rest of your joints carrying on from there go out here to wherever your end effector frame is. So this is my end effector, let me just call it epsilon, kind of a squiggly E. Right? I don't like to use regular E because it looks like error. So I'll use squiggly E for end effector. So I've kind of got all the way to go from here to here and then from here to here. Now if I change DI how does that change E in just the linear movement sense? If I displaced it a little bit more up here, di was a little bigger, then you would just take the same exact effect here and carry it up, right? Can that possibly rotate this?
No.
No.
No, it just shifts everything. If this is that little, whatever we want to call it, delta D3 that comes on, that's the same thing all the way through. We agree?
Right.
So the change in that end effector thing from this is just the end effector has been moved an amount delta D, the change in whatever you've done, in the direction of Zi minus 1. All right? This delta dx is my d dot. How has it changed? All right? That's the change. That's what d dot is.
Right.
All right? Times this. Well, in the linear direction, it's this delta dx in the Zi direction. So it's the d3 dot in the Zi minus 1 direction. We agree?
Mm-hmm.
Because that's the direction it's traveling in, the amount of the change, the dot.
Is that delta dx?
I was just saying this is some change, delta
Okay.
d. Well, it's just, it should actually be di, really. And in this case, it was 3. It's the amount of change in the di-th component. So di was di, it changes a little bit, it becomes di plus a little something. And what that change is proportional to the derivative. Because you just take it, we're taking smaller and smaller amounts. So if you take the change in di, limit as it gets smaller and smaller and smaller, you've got the derivative. That's the definition of it. Take the limit as your change goes towards 0, boom. All right? So this part right here is the variable. Right? That's the part that's here coming in. And remember, our Jacobian was translating from these to the global coordinate systems. Change in x, change in y, change in z, change in the thetas. We agree? So what we're saying is the change over here is this in the linear direction. But that is the vector times this. So therefore, this must be the Jacobian component. We agree? Yay. Makes sense, right? I mean, all we're saying is the amount that you have changed it by in the direction you have changed it, that's the change. Right? And this, we're pulling out into the vector. What's left goes into the Jacobian. So this part right here, the linear component, has to be Zi minus 1. Do we agree? So if you think about this, right, the ith column of J we have now figured out is Zi minus 1, and we haven't, for the upper part, we haven't figured out what the lower part is. Now let's just discuss for a second, what is this? Right? When I talk about Zi minus 1, how do I get that? I mean, it was pretty simple to write once you drew the picture. But what does that mean? How do I get the components? So think now for a sec, to know what that axis is, that's the axis that I'm moving in the direction of. It's not pointing in terms of the global Z. It's in terms of some local coordinate, Zi minus 1. And that axis has components in the global x, y, and z. So you got to remember, I have lots of x, y, z reference frames that are going on here. There's only one global. This is a local frame. And I'm saying the z-axis in the local frame. So when you calculate your t, and I think the book goes u to I, is that what it?
I think it's h.
Or, but we only want to go up to I minus 1.
Okay.
Right? But I think they said start here, go to here. Different people do different ones. Some people do that, some people do this. I don't remember what your book used.
The book does the other way.
That
On the
does it
left-hand
over
side.
here. Yeah, it's going from you to here. Yeah, I thought that's what they did. So when they're telling you this to go from here, and remember we said we had calculated that already. Because if you have the table of the DH parameters, you can easily calculate this. You just take the first several rows, make the transforms, multiply them all up, all the way up to I minus 1. That gives you the coordinate system starting at I minus 1. And that components, when you look at it, it's got the rotation matrix, which is the upper 3 by 3, a 0, a 1, and it's got a position matrix, right, which is offsets. And then in the rotation one, it's got the NOA coordinates. But if you think about it, NOA is just another way of saying the local X, Y, and Z axis. This is X, I minus 1, Y, I minus 1, and Z, I minus 1. That's where you started. And this, Zi minus 1, is the one we're sticking in there. What is, in global terms, because this is global directions, what is the Z-axis for that particular component? Where is it? It accounts for any joints up to here, how it might have twisted it, rotated it, aligned it as it goes. That was all taken care of by this transform. Globals to the I minus 1. So all we need is the third column minus the 0 on the bottom. Make sense? And we just pull that out and we just stick it right in. So if you ever wondered why we made you calculate all those little, U to I minus 1s, this is why. It gives us the ability to get the Jacobian very easily. It will actually turn out that is going to appear a lot of times. So far, so good? Okay. The linear motion of this actuator, how much does that rotate this?
0.
It doesn't at all. So the effect of that motion on the angular movement is 0. It doesn't do anything. So if your ith component is a prismatic joint, that is exactly what the ith column of your Jacobian is going to be, which you can easily get from your forward kinematics from the DH parameters. Okay? So it's very straightforward. Don't miss it. This is part of why we like DH. Remember I told you the disadvantage was it's not very robust, right? If there's manufacturing errors, you better remeasure everything. But once it's done, you might go, hey, why did somebody want to do this in the first place? Well, besides all the other simplicities we showed, here's another one. It's very easy to get the Jacobian. We've shown it for one. Let's do rotational joints now. Okay. But do we feel good with prismatics? Very good. All right. Same type of a thing now. I'm going to imagine my particular ith component is now a rotational, because I realize this was 3, so you can pick I to be equal to 2 or whatever you want as it's going. But I'm picking one of the ith component that happens to be rotational. And I'm going to start doing the angular momentum one because it's a little bit easier to calculate, and then the other one we'll figure out. It's slightly more work, but it's still not bad. It's got a z-axis. So if I'm talking the ith one, it's zi minus 1. I'll leave this up because I still will need it. Right? So I've got zi minus 1, and the next component, if I had extended it, the xi minus 1 was pointing this way. So any small change you do is going to cause it to rotate like that. All right? We agree? Now originally, this one would have gone in the direction of x. I'd go up and over, and then I'd do some rotation of the z to get the next one. But once I rotate this, it's just going to rotate that by the same exact amount. Right? Do we agree? Mm-hmm. Okay, so when you then consider that one as it's going on, okay, there is some type of a motion that's going on here. If I'm going to describe a rotational velocity, right, all of you have had, or a lot of you have had vector calculus. As everybody's had the E and M, right?
Yeah.
Do they, when they do E and M, do they do it with vectors?
Yeah.
Okay, so then when you get to that, you get to the waves, do they deal with the rotational vectors in that way? Or even in 221 when they do torques, and you got something that's rotating on a torque and they deal with what's the angular velocity of
Yeah.
something rolling down and it hits a curb and it bounces up or whatever,
Yeah.
right?
Yeah.
What is the direction of your angular change? If I have something, some sphere is running on and, I'm going to say that, it's rotating at a speed omega, right? Or it's gone through a change of theta, whichever way you want to consider it. I don't care whether you want to consider speeds or whether you want to consider a positional change on it, an angular position change. I'll just do omega because I've got it here and that's what we're dealing with. Right? What's the direction of that omega?
Coming out.
The right-hand rule.
It's out of the board.
Right.
Right? We always say it's in the direction of the axis of rotation, right? Just strike a bell from your physics?
Yeah.
Okay, so since it's in the direction, this angular change here is in what direction? It's in Z. It's the axis of rotation that you are doing it. Okay?
Just to make sure I'm understanding the painting you're drawing, you're
This was the
rotating into the
original.
board. Are you rotating into the board or up?
Right? I'm rotating about this axis right here.
Okay, so it's
which could be,
the board.
it's not necessarily in the direction, it could be in, it could be out, I don't care where it's, I'm just saying there is some Z,
Okay.
right?
Yeah.
So that Z could be pointing this way, that Z could be pointing this way, I don't care where it's pointing.
Yeah.
But you're rotating about the Z, whichever direction it happens to be pointing. And you are going in the normal thing we always say counterclockwise, right? Is the way we've always measured as it goes. And this comes up again and again in physics when you do your, Green's theorem and stuff like that. You calculate an area, right? And you always take the, enclosing surface. It's always in the counterclockwise direction. Because that's the way we always go. It's counterclockwise. It's convention. But you have to be consistent once you've set that up. So we always do counterclockwise. So I'm saying this, whatever direction Z happens to be facing, and I'm rotating in the conventional way that is associated with right-hand rule, right?
Yeah.
Fair?
Okay.
Okay. So think about the rest of your frames that are going on. Originally it would have been whatever here to some end effector epsilon. Now it's gone through a motion, but that motion is based on that rotation. So the amount of angular velocity that has been encountered here is exactly the angular velocity that was here. Doesn't matter how far out you are, it doesn't matter the lever arm. That'll affect your positional, your linear velocity, but it will not affect your angular velocity. Do we agree? Yes? Am I going slow or fast? Because there's an awful lot of people who are just kind of like, right? And I don't know if the coffee machine broke, if I'm going fast, if I'm going slow, right? So if I'm going slow, I'd rather speed up. If I'm going fast, I gotta explain something more. I think I'm just reminding you of stuff.
Yeah.
Yes, good?
It's a good speed.
It's a good speed for mine, okay. So we agree that then the change that's happening here is the linear, or is the angular velocity change up here, right?
Yes.
And that change is, right, it's going to be the theta sub I dot, right? How much you've changed it. Now notice theta sub I dot we often just call omega sub I. Right? That's the magnitude. The direction is going to be in the direction of zi minus 1, in the direction of the axis it's rotating about. Because remember, when we give a direction to a rotational vector, it is always in the direction of rotation. And our rotation vector is z. By convention, it's always, always z you rotate about. Okay? You can change that new z to any other thing you want by doing an alpha rotation later on, but it's going to be the local z you rotate about. That is our rule as it goes. Therefore, this is the joint parameter. That's the part that sticks out here in the vector that's going to multiply j. This is the total answer, so this must be j. That's got to be the Jacobian in the angular part. Make sense?
Yep.
So now, that was for prismatic joints. For rotational joints, The J for the rotational is Zi minus 1. Agree? Yay?
Yeah.
Okay. So that was pretty straightforward and simple. Now we want to get to the next thing. Now I need to know, this picture stays the same, right? But now we want to find out from this rotation, the actual effect that's gone on here is there's, in essence, an instantaneous velocity that's going on in a positional sense over here on the ends. How do I get that? If you just have, imagine I've got this picture here, right? It's rotating about this, and I said, you know, it's got some radius r, and I want to know what was the linear motion of this that's caused by rotating omega.
Yeah, because you get the
So I would agree it is in some sense omega r, but there's a little more to it,
Is it dark?
right? Well, I want to know in a vector space what it is. So omega r works nicely for the magnitude, right? But it doesn't tell me the direction, right? Because omega r, that's how big it is. Do we agree with that?
Yeah.
So you calculate it by the cross. You take omega as a vector, you take r as a vector, and you cross the two vectors. So if you think about this, this gives, why is it this way? How do you know it's tangent?
Well, now it's because it's a cross product.
Because it's cross product.
Orthogonal.
Right? The rotation is coming out here.
Okay.
This one's here. That has to be 90 degrees or pi over 2 to both.
Right.
In the right-hand rule sense. You just put your hand up there, contort it into the silly directions, right? Sticking out the plane, pointing at r, so everyone's got to be that way. Which gives me where that's going. So if you do omega cross r, you not only know the magnitude, you know the magnitude and the direction. So I have a complete solution. Okay? So I agree, omega r is, you know, kind of what most people think about. It's the magnitude as it goes on. But we now kind of need that extra little step. Do we all feel good about that?
Yes.
Okay. So if you think about that then, what I need to know, that has to be the same for over here. Well, omega is my theta sub I dot, right, in the Zi minus 1 direction. That's omega. We agree?
Mm-hmm.
Yay?
Yeah.
Right? And I've got to cross that with r. So now the question is, what's r? Well, r is the vector that goes from here to here. Right? From this part to this part. That is your r. We'll put it in physics notation. Put its funny little hat on top. Right? So that's r. Do we agree? Mm-hmm. From where I'm at to the end, right? Because my end effector, I don't care how it's bent in between, right? R is that straight line distance.
Cool.
How do I get that?
That's your x, right? That's your
But
next.
from what? How, right? I've got two things, right? I know this distance from here to here, right? I get that from u to ti minus 1. That's this right here. That's this vector here. Pi minus 1. All right? This part right here tells me how to go from the global origin to the origin of where my rotation is.
Right.
Just spatially. It's not saying how it gets twisted or anything else. That just finds the location of the origin, how it's shifted in space. Do we agree? Okay. But how do I now know this?
That's your next p, right? P sub I.
Well, what if I know? Well, that takes me to some other little joint here.
Okay, so the whole thing, I mean, that's correct.
Ah, so if I know u, t to the end effector, however many joints that is, right, that's going to have a rotation matrix 0, a position for the end effector, and a 1, right? And that tells me whatever this vector is, right? I have to kind of draw it a little funny because it's semi-in line on here. right? But this is the vector p to the end effector. So how do I get this component?
So cut pi minus 1. From
So what I've got for this r is p of the end effector
minus pi.
minus p I minus 1. But I can read that right off the global transform from the origin to the end effector. I should take the last column minus that one element down at the bottom. And this one, I just go to the same thing and pull the last column, all except for the one on the bottom. Take the difference, cross it with this. That gives you the total motion. Do we agree?
Yeah.
And that'll give you the motion that goes on in each of these directions, right? In terms of this. Well, I can pull this theta dot I out, can't I? That's a scalar. Do we agree that this is the same as doing this? I can pull it out of the cross product without any change. And I can do this without any change. I can decide to calculate the cross product first.
Yeah.
But isn't this the component that's coming in from the vector? So if that's the vector, what does this have to be? The Jacobian. So the missing component up here, it's a little bit bigger. I told you it'd be slightly more complicated. It's zi minus 1 again, this time crossed with whatever your p vector is to the end effector minus your p vector to the origin of the current frame. Done. I now know what a rotational joint's Jacobian looks like. So since our robots are made up of rotational joints and prismatic joints, all you have to do for each one is you just write it, you know, it's an R, R, P, whatever, as it goes on. And for each one, you just kind of grab the component and stick it in. It's straightforward. I mean, at this point, it's plug and shut. Now, the reason why I want to hammer this in detail is the book gives you the numbers in the Jacobian, and they say, here's a Jacobian. And they never tell you why they got at least the version that I have. I looked at it real quick because I didn't remember them doing it. I don't know if they fixed this in the newest version, but in the version that I had, they just said, here's the Jacobian numbers, right? And then tell me what is the motion. And yes, indeed, you can do that. That is checking to see that you can calculate.
Yeah, so
Okay?
that's something you give to the computer.
But what they
after the
never
stupid-
did, at least in the version that I've only have the first edition left out, they never said how on earth they got that Jacobian. Right? And that kind of always bugs me. So I wanted to at least give you the way, how do you get that Jacobian in the first place? Because otherwise it's kind of a semi-useless piece of information. If somebody happens to calculate 2/3 of it for you and says, oh, by the way, can you calculate this drudgery, you can do it. Now you can do the whole problem. All right, so the book gives you a lot of examples starting from when you've already built the Jacobian and finishes it. All right, so if you want, we can actually do an example where we can calculate one of these. Hopefully we'll pick something a little bit small because it's just tedious. But the idea is here. Do we feel good with the idea and why it comes up?
Yeah.
And therefore it's pretty straightforward to be able to get something, right?
Yeah.
Can you do an example like
That's what I was going to say. Do we want to do just a small example to see something?
2 or 3 joints? I mean,
Yeah.
rotational and prismatic joint, just so we can see both.
I agree. That was my plan. But I don't want to proceed into it if people don't get where it came from in the first place. Is everybody going to remember these?
Yeah.
Yeah.
Okay. All right. Is it okay if I do a really small robot? We'll just at least for first, we can add on more if we want. I'll just do a rotational and then a prismatic. Right? So the idea of our robot will be, and I'll do it in 3 dimensions, but in effect, all I need is 2 when going on here. we'll have kind of our, I'll call this X, Y, Z as it's going on. And we're going to have, in the initial Z direction, we're going to be able to rotate. And then that rotational joint will head to a prismatic joint. Which can then extend out. And at the end of this will be where your end effector is. So the idea of this is, right, imagine I've got a hydraulic cylinder sticking off the side of me, right? So I can rotate and extend. So looking down from the Z direction, just on the XY plane, you've got the ability to set the angle theta, and you've got the ability to adjust the distance R. Right? This joint is going to be able to handle your angle theta rotations, right? And then this joint here that's sticking out is your angle R, and this is a hydraulic cylinder, right? So it can extend.
Right.
Does it make sense, the idea of what's going on here? So it allows me to basically get anything in two space, presuming that your extension is able to be long enough. We all feel good about the road. Okay. First step is we need those DH parameters. Okay? So I've already got my coordinate system defined up. So my very first coordinate system, I need to go from 0 to 1, which gets me from this original coordinate system to the one that's here. Now Z has to be pointing down the axis of this that's going on. All right? And so from there, I'm going to have, all my other things, right? My X, Y, Z's handle it. We feel good?
Yeah.
That goes on. Now, so I'm going to have this, and it's going to have to carry up, and I'm going to have to rotate Z in. There? Okay. So for my first one, we have to calculate our theta, our D, our A, our alphas. All right? So far, so good?
Quick question.
Yeah.
If the Z is going to be pointing down the prismatic joint that way, which way would the X be pointing? The X-axis?
Yeah, so that's a good question as it goes. So the question is, in essence, how do you measure on these as it happens? Usually what we do is we assume there's an initial rotation of 90 degrees on it, so that we have this pointing kind of in the Y as it's going on, and then it'll be pointing out to the side.
So, yeah, okay, so X wouldn't really change. So Z's coming this way, X is still...
It's just a straight, right? If I'm rotating this part here, does it matter whether I measure it from here or measure from here, how far my rotation
that's
is?
not gonna change.
It doesn't matter a bit. But if I call this X, and this is Y, it's just theta plus 90 or theta plus pi over 2. Right? The theta is still the same as it goes, but now my X is going to be off to the side so I can then rotate in.
Yeah, okay.
Does that make sense? Mm-hmm. So that's a very good question, and it'll answer why I'm about to have a shift of pi over 2 in here that's going on. Because what I really want to do is actually measure this rotation from there, from the Y. Right? I mean, you can technically measure it from there, but it's easiest if you measure it from the Y, as it goes in this particular case, which just means the angle is theta plus pi over 2. Good? So my initial one here is going to be whatever your theta 1 is. Right, that's your rotation, plus the pi over 2. That gives me the rotation, so my X is sticking out to the side. Yeah? All right. Now, since these actually project onto each other, there's a point where they hit, and we said we're staying in the plane. So therefore, there's no translation along that I have to move. As a matter of fact, they're going to hit right on this axis. So my next one's going to be on the axis here, so it's going to be at the same origin. And then all the movement will be along Z in the direction there. So my D is going to be 0, because there's no movement in the Z direction. Is there any movement in the A direction to get to the next coordinate frame?
Yeah,
No, it points right at the origin. They have the same origin in this this case. Right? Yeah.
Why do you have the power of 2 again?
Because what I'm saying is I need to do a rotation to take this Z down in the direction of here. So I can't make X point in that direction, because then I couldn't rotate about X to get Z pointing down the origin. So what I want to do is, I said, hey, what if we just made this whole thing, in essence, measured from a Y direction, and I just stuck Z off to the side here, X off to the side here, so that now I'm pi over 2 plus theta to get to there. And the base position is here. It doesn't change the angle, but it gives me a pi over 2, a 90-degree shift, which then when I want to rotate about X, I can rotate Z down into the new Y direction. And that can be done very easily. All right? So again, remember my situation was here. All right? I'm looking here, I've got a prismatic joint that it can extend out and I can rotate. What I call my first direction, whether I call this X or I call it Y, or whether I call it, X plus Y, all right, where you start is completely arbitrary. So you pick something that's easy for you. If I call this the X direction, there's nothing illegal about it, and it kind of makes some sense at first. But then at the next stage, since I'm going to want to call this Z, but I'm only allowed in DH to rotate about X to achieve that. If this is X, and I want to make it Z, and I can only do that by rotating about X, I'm screwed.
Yeah.
Okay? You can't rotate about X. I could rotate Z into Y, but I couldn't rotate about Z to get into, or rotate about X to rotate Z into X. Because X doesn't change if you rotate about X. So I said, oh, what if I called this X and I called this Y? All right? So now it's just a different change. I still have Z that I'm rotating about. If I do that, I can now do my rotation still, except now my rotations are theta plus pi over 2 because I was measuring from X. Right? The 0 position is just the pi over 2. So my angular rotation is still every bit the same. You just have to have an offset, a phase shift. No problems there. But now when I want to get my Z, the direction of my head, to point this way so I can extend, and I can rotate about X, all I have to do is, and I'm fine. As a matter of fact, it's a 90-degree rotation, isn't it?
Yeah.
All right? So by choosing a different coordinate system, I go from not being able to do it to being able to make it very easy. All right? Now, could I pick any coordinate system I want? Yes. Are all coordinate systems equally good? No. Some ones will naturally fit your problem, others won't. So you have to choose wisely as it goes on. Otherwise, you get to a point and it doesn't work. And if you get to the point and it doesn't work, you go, oh, I need to go back and change. And that's just because you picked it such that you have a singularity. This is something they usually talk about a lot in physics, what if you have a singularity in your direction. Yay. They talk about that.
No.
People stare at you blankly.
Sorry.
It'll come up often in other areas where they'll talk about things. For instance, when you take the, you do like a derivative of potential energy. Force is in the negative direction of potential energy.
Yeah.
Change, yeah, right? Those type of things. So you'll sometimes find out when you solve problems that if it wasn't a conservative force, right? But you assumed it was and you try to solve it, you'll end up getting that it doesn't work. Right? When you try to solve for that force or when you check, was it correct from your assumed potential energy, you'll find out it doesn't work. It was a non-conservative force. So therefore you find out, hey, I can go through all the things, but if I didn't start with the correct set of assumptions, going through the mechanism will end me up at garbage. Right. You have to start from the right spot and follow the mechanism, and that's all I'm saying to you. If you pick a coordinate system that's kind of in a bad direction, right? You're trying to rotate about X to pull Z into X, it just can't happen. It's a physical impossibility. You chose a bad coordinate system. You just got to realize, oh, I can't do that, and so you stop and you go back and you find the one that works. Okay? So it's the same thing you would do there with potential. There's a lot of other ones. You have to choose the correct setup of the problem. Yay?
Yep.
All right, so that it does appear as you go through. All right, how much is A change? Nothing, right? Because we're still going about the origin. How about alpha?
Is that hydrogen?
All right, so I've got to rotate about X to pull Z into the direction of Y.
Negative 5.
All right? Yeah, so if I was rotating Y to Z, all right? So rotate about X to pull Y to Z, that's pi over 2, right? To go from Z to Y,
Negative.
it's minus pi over 2, isn't it? We agree?
Yeah.
All right. So yes, you will get a very flexible wrist. But the right-hand rule is very important to us, okay? So now we've got it pointed, so we are in the correct direction for our axis here. All right? So our X is sticking out the side, and our Z is pointing down the axis, and Y you just get by the cross. Now what do I have to do? Next one.
Yeah, I have to move there.
Now I have to do displacement. Is there any rotation I have to do? No rotation necessary. Displacement in this direction. Right. So now this is going to depend how you want to measure this, right? In our case, I just said R is that whole distance.
Right.
Right? So now you could say that it is, that there's a base offset to where you put the hydraulic thing, and then how far did you extend the hydraulic. You could break that up into components, and R constant plus R changing if you want to. I'm just going to call the whole thing R for simplicity, but realize there's a fixed amount to where you mounted the thing.
Right.
Plus, there is a certain amount that it actually changes by, did you pull it to its own 0 setting or offset.
So you're just saying just
So,
go to the end of that.
The same thing that's going on here, right? There's a variable amount plus a fixed phase shift. The same thing happens here. There is a change in the hydraulic joint, plus the hydraulic joint didn't start instantly right at the origin, right? I had a little mounting bracket there. That mounting bracket added distance. So realize there's a constant on here, just like I had a constant phase shift here. Right. But this is really one angle, isn't it?
Yeah.
So by the same token, this is really one displacement. Just realize it's made up of 2 components just like that.
Cool.
Okay. Any shift in the X direction?
No.
Do I have to rotate about X any?
No. You're set.
Here we go. So far, so good?
Yeah.
Okay, so now I can calculate my transforms. To go from 0 to 1, what do I end up getting? Right? Or we can call it U to 1. How do I calculate that?
Your position
The rotation
of theta.
about Z of theta, right? Times the translation in the Z direction of D, but that's 0, so translation, right? Translation in Z of a distance D, which is actually 0 in our case. This is
0. Or 1.
an identity matrix. It is one, it's the matrix version of 1, right? But we call it the identity matrix. Translation in the X direction of A, which is 0. Right? And then we need a rotation about the new X of minus pi over 2. Right?
Would the first rotation be theta plus pi over 2?
Oh yeah. Well, I'm just saying that whole
Okay.
theta 1. I'm trying to be lazy by just going that theta, right? That angle. So I was just using this name up here. That's why I didn't put a subscript, right? The respective theta. But yes, you're correct. That theta is theta 1 plus pi over 2.
Boy, that marker budget must be intense.
It's my laziness budget, actually. But realize that's why I call it R.
Yeah.
Right? Because, I was avoiding writing the whole matrix out. Shorthand helps you. And my point was, if we write it kind of generically, we just remember it's always rotation about Z, translation X, rotation X.
Yeah.
So if you keep those in mind, we're good.
That's an R at the end.
rotation about x and of amount of angle minus pi over 2.
Right.
I never said I had nice handwriting. Right? That's why I got a PhD. People go, wow, you must be a doctor. I'm like, okay, I guess I got to get one. Okay, so these ones are gone. So I just have these two rotations. Those two rotations, this one is a cosine of theta 1 plus pi over 2, and a sine of theta 1 plus pi over 2, and a minus sine of theta 1 plus pi over 2, and a cosine of theta 1 plus pi over 2. And this was rotating about z. And then we have the general setup, and there was no displacement. That's the first rotation.
Right.
We agree?
Mm-hmm.
Times, now we're going to rotate about x, so I have to put the rotation axis out first. Maybe I'll not put that 0. Make this a little bigger. It's going to be hard to fit my numbers in there. There's no displacement. And we just put our cosines and sines in here. So now I've got cosine minus pi over 2, sine minus pi over 2, minus sine of minus pi over 2, and cosine of minus pi over 2. We agree? Cosine of minus pi over 2 is?
Minus cosine pi over 2.
Yeah, but what's cosine of pi over 2?
0.
No, what? Wait. 0. 0. 0.
So, I mean, when you said that, you know, cosine of minus pi over 2, right, is equal to cosine of pi over 2.
That may have been a 2.
That is true, okay? Well, that's just they're both 0. But I mean, the general thing does hold that the angles do reflect around there. But in particular, pi over 2 is 0, so we can get a little bit better here. This has to be 0, and that has to be 0. How about sine at minus pi over 2? That's negative 1. And minus of that is 1. Huh? So this is kind of a nice matrix, we agree? Huh? So this one, we often call this, and if you ever get into quantum computations or a lot of quantum stuff, if you see this little kernel inside of a matrix, we call that phase shift. Right? And you should just realize why at this point, because a phase shift of pi over or minus pi over 2 gives me this matrix. All right, so this is the minus pi over 2, and the pi over 2 just gives you minus 1 plus 1 there. So that's called a phase shift matrix inside quantum computation. Just give you some free side bits on matrix notation. But that's an important one. If they're both 1, we call it a reverse order identity. So if you plan on going further on, these all have names, and they have significance. The fact that they're flipped is going to reverse 2 of our ones. It's going to flop in this, or flip in this case, the y and the z axis, and negate one of them. So it's flipping 2 of your axes, but that's what we just did, right? We wanted, this last part was supposed to flip the z-axis into the y direction, and the y into the minus z direction. So that it does that, is kind of reassuring. We realize that's important in a lot of other areas, so we often name it so. All right, so do we want to do this multiplication?
Sure. Or, yeah.
Why not? Okay, this is one of those cases. Remember I told you there's several ways you can multiply? In particular, there's easy ways and hard ways. This is one of those ones that my shortcut comes in very handy.
Because there's lots of zeros and ones.
Why? You actually don't need to. I mean, you can if you want. I mean, right? This is pi over 2 shift onto there, so it's shifting it to a sine, right? So you could switch these and realize you're switching cosines and sines, and you have a little bit of a sign change. Okay. You know, and if you want to do that, that's awesome. You know, I don't see a huge need to it, but it just takes up less room. Yeah. Yeah. I mean, if you want to, we can. I mean, just remember when you're going in here. Here's your sine. and here is cosine that's going on. So if I've got cosine of some angle plus pi over 2,
It's just sine.
right? So I've got cosine, right, of an angle plus pi over 2 means I'm really starting right here, in essence, right, a pi over 2 shift. I'm starting here, so it looks just like negative sine, doesn't it? Of just that angle. So you could swap this one out, and if you felt like it, you could remove that and get minus sine, and dump that. All right, and sine, if you were looking at it, shifted over to here, right? Right, that's the pi over 2, and then you're starting your angle from that point. It looks just like cosine. So, you can do that if you want to save a little space. I agree. So if you remember, whenever you see the pi over 2 shifts, they're fairly easy because it's just shifting the axes. Right.
Should there be a negative on that bottom cosine?
Why? Because it was.
No, because
This one has the negative because it was minus of sine
Oh.
beta plus,
I thought there was a
and
minus
this
there.
one was sine.
Yeah.
Right. So when you're taking sine of theta plus pi over 2, right? It's the same as looking at, right? The pi over 2 gets you to here. It looks just like cosine of that angle without that pi over 2 shift. Right, so it gives you the same net effect. So the sine goes to cosine with that shift, and cosine goes to minus sine. Okay, good? So yeah, I mean, you can simplify it, but you don't really have to if you don't want to. Remember my shortcut on here? This one is going to generate the first column, right? But it's not taking any of these last ones. It just says copy the first column. So the multiplication is fairly easy. The first one just copies it. So I've got minus sine theta 1 cosine theta 1 0 0. That's what that one says. And what does this one say? It says the second column is going to be negative the third column. Right? And the third column's right there, so it just goes 0 0 minus 1 0. There you go. And then this one says the third column, 1 2 3, third column will be the second column. And then this one says the fourth column will be the fourth column. That wasn't bad to multiply, was it?
Nope.
Remember I said, if you've got a matrix that has a whole heck of a lot of zeros in it, right? Taking a look at this as saying, you know, how much of the first plus how much of the second plus how much of the third plus how much of the fourth to make up the first column makes sense because there's lots of zeros, so you don't have to actually do a lot of that addition. Okay? Could you have done this by multiplying through? Of course you could have. Would it have been as fast? No. So it's a speed, not an accuracy issue. As an added note, if you are a computer scientist, this is actually the basis, recognizing this, of what goes into sparse matrix notation. And so that does a lot of speed up and parallel computations and things. So this type of a recognition becomes very important for speeding up your calculations. Good? So now I've got the first part of this done. And realize what I really want is this right here. Right? This is Z1. Okay? And notice that my P1 is right here that's going on. Now, what is, notice I said this is Z1 and P1. Where is Z0 and P0?
0. They're at the origin.
0, 0. Yeah, they're right on the order. Well, this is actually 0, 0, 1. It's just pointing in the Z direction.
Yeah, it's like that.
Right? And then this is all zeros for P0.
Yeah.
So, by definition, Z0 is always equal, because it's the global coordinate, it's always the global coordinate. It always, always, always is in DH. Right? It's nothing profound. It's saying the global Z points in the direction of the global Z. All right, it's a tautology. Right? And the P0 is just equal to all zeros because it's just saying the global origin is the global origin. Right? So again, tautology. Given that, do I even need to calculate the next one?
Well, there really wouldn't be any calculations. It's just going to be matrix, but
There's a translation, but you do need to calculate it. Why?
Need the final distance.
I need the overall distance because I've got a rotational joint which is going to affect my linear velocities for that revolute joint. So I need to know the global position of that final end effector in order to use its position to calculate the lever arm that you are rotating against. Okay? So therefore I'm going to do an intermediate one, which will be pretty easy, going from 1 to 2, or 1 to E if you want to consider it. Right, the end effector, just so we remind ourselves. Okay? And it'll be a pretty easy one to do. Because theta is 0, so that means the first revolution is identity matrix. It's like multiplying by 1. The next one is displacement of R in the Z direction. I have to actually write that one. So I've got an identity 0, 1, and then 0, right, 0, R. And this is a 3 by 3 identity matrix. Okay? How about a translation in the X direction of 0? It's an identity matrix, so it doesn't change anything. How about a rotation about X of 0? It's an identity matrix, doesn't change anything. So 1 to epsilon's right there. Right? So, but I don't want 1 to epsilon, I want U to epsilon. So how do I get U to epsilon? It's really easy to check these, right? You just go U to 1, 1 to epsilon. These have to match inside, and it goes from U to epsilon now. Pretty simple. All right, but we already have U to 1. It's right here.
Couldn't you just put the 1 to epsilon in front of it and then just multiply it straight across and see where you had it there? Save yourself ink. Couldn't you just put that matrix right there next to it instead of
I could have stuck it right here.
Well, you could have put it right there too. And...
Well, you can't multiply on either side.
Oh, right.
Right.
Then you could put the inverse on.
Yeah, so, I mean, remember, again, this one is happening after, so I must multiply on the right. The only way you can exchange, remember I said you can exchange these two? It's not because you're exchanging a rotation and a displacement. Mm-hmm. You're displacing a rotation about Z to a displacement in Z.
Oh, okay, as long as you stay in the same.
It's because they're on the same axis that they can then change, because a displacement in Z is independent of the rotation. Because the Z-axis here never changes, so therefore the displacement doesn't change, so it doesn't matter whether it happens first or second. Right. But if you're doing a displacement against something that does affect the Z-axis, now you're no longer quite so free. So let me just record this because I'm going to erase this in a sec. So I have that Z1 is equal to minus cosine of theta 1 minus sine theta 1. And we know our P1 is all zeros also. So therefore I can erase this because I got the part out that I needed. So then I have to multiply this by that. So So now I'll actually write all the components out, such as it is. We agree?
Mm-hmm.
And again, notice an awful lot of zeros. So what's going to be your easiest way to do this?
The Schubert way.
Yeah, they just copy the columns in this
Do you
case.
actually have a name for it, or is it just the Schubert way?
A lot of people do this. I've seen a lot of people do it, but I've never seen a name attached to it. So there might actually be a name. So I wouldn't actually call it. There are people who noticed it before I did, right? But it's not often something people teach in the lower classes. So I just want to, I always believe shortcuts help, particularly if they're informative.
Right.
Right, so what this means right here, if you look at the first three columns, it says what was the first column becomes the first column.
And then second.
What was the second becomes the second, what was the third becomes the third. So I just keep them all, right? Just saying keep those ones that's on there. This is the only one that's going to cause any change. So the first three columns are the same, so I can just write them down. So that's the first three columns caused by first three here. And then it says, keep what was there before. Well, that's only a 1 down here. Right? This one says, keep the old last column. And add to it R times the earlier. Right? And the third one in particular, so it's R times this. So nothing changes here, but I do get minus R cos theta 1 and minus R sine theta 1. Right? And what I really cared about was this, which gives me the length of my arm. Right? Because that one gives me the position of the end effector. Yeah.
If we were doing this on a test, then we can easily just see that the R will give us that. Do you still want us to go through the trouble of
No, so
writing
I don't
it?
give you a calculator on this because I don't want to check to see do you know how to multiply numbers.
Yeah.
Right? I want to know that you can set up a problem.
Okay.
If you can write the problem, if you correctly define everything and show me how, I wouldn't expect you to multiply. Unless it's pathetically easy like this. If it is pathetically easy like this, multiply it. Right? If it's something jumbled and ugly as hell, then no, I wouldn't multiply it. I would just say I would multiply at this point. Okay?
Insert MATLAB here.
Yeah, you know, I mean, do MATLAB here. I mean, as long as you know how to do that, then it's a simple step. You know, why do I need to check that you can enter something in a calculator? Okay, so that's kind of my opinion. Everybody has their own opinions, but that's mine. My concern is, can you set up the problem? I will check, can you, in the homeworks and whatever, that's where we check, do you know how to enter it into MATLAB? You know, or whatever else you want to calculate it on. Understanding some of these copy things will sometimes help you, like if sometimes you're in the lab and you're working on something and the computer's not easily accessible there, being able to look at something, writing up on a whiteboard is a good skill.
Yeah.
Okay? So, you know, you ought to be able to do simple multiplies like this. If it gets anything complicated, step over to the computer, program it in. Might be done with this. Because you're likely to make some silly mistake. Because I'd make a silly mistake. It's part of life. Okay, we good?
Yep.
So now I want the Jacobian. What's the Jacobian going to look like? How many rows, how many columns?
4 each?
Well, I've got a three-dimensional space, right? That's going in. So you've got an X, Y, and Z displacements that could happen. And you've got rotations about those. So the number of rows is going to be equal to the number of actual linear displacements plus the number of angular displacements. There are 3 linear, there are 3 angular, so therefore I must have 6. So this is going to have 6 rows, right, for the X, Y, Z, and then the rotations, respectively. Good? How many columns?
So X is going to be 4.
I don't know who said it, but whoever said it was right. Right? Why 2? Because you only got 2 variables. Right? you're trying to find out how small changes in theta, one variable, or small changes in r, your other variable, the two things you can control, affect changes in x, y, and z position, and your rotations. Right? That's all you care about. Right? Yes. Okay. So, the first one, rotational or prismatic? It's rotational. So to get it, I need my first z, which is z 0, crossed with p epsilon minus
P1.
the p0, right? Your very first one that goes in. Right? How far is your lever arm?
Right.
Right? And then down here, I just have z0. And z0 is?
0, 0, 1.
Right? So I can replace this down here with 0, 0, 1. And then I have to calculate this cross product. Well, p0 is zeros. Right? So trivially, this reduces to just p of the end effector. So I just need z0 crossed with p of the end effector. We agree? All right, so we can calculate this. Number of ways you can do it. We'll just do the standard ijk, take the determinant thing. All right, so I need z0, which is 0, 0, 1. And my PE, which is right here, which is minus r cos theta 1, and minus r sine theta 1, 0. Take the determinant. It's starting to fade. All right. So, everybody remember how to take determinants?
Yeah.
So this is I times determinant of
0 minus
I.
negative
You
r.
take this one, you remove the row and the row and the column, and you're left with the determinant of the sub area. I'm going to write it out, even though we technically could just do it, because I'm presuming some people have not done this, or at least in a while. Is that an accurate assumption? Okay. Then we go minus j. Why do we go minus j?
Alternate.
Every other one you alternate the sign. Right? So you do plus I minus j plus k. If there was more, you'd keep alternating. Right? Minus j times, and then you remove it and you squeeze together. So I get 0, 1 minus r and the 0. So 0, 1 minus r cos theta 1, 0. And then plus k. Remove it out, and we're left with this. Theta 1 is r sine theta 1. All right. Now I'll do one of these for you. I'll do the last one. All right. All right. 0 times this is 0. Minus 0 times that is 0.
Very good.
All right. Hey, I did a third of it. I didn't even set it up, right? Plus k 0. Somebody else help me with j now.
Negative r cosine theta.
0 times 0 minus
Minus
1 times that, so it's minus a negative, and you get
R cosine.
r cos theta. Not that bad, is it? How about this one? 0 minus, you get r sine theta 1. Agree?
Mm-hmm.
So then reconstructing this, right? So this is the way we always do the cross product. We write it as if we're going to be doing quaternions. We get the result because of quaternions, and then we just convert it back. So we just go, this is a vector. This is my x component. So it's a vector that's r sine theta 1 minus r cosine theta 1 and 0. And amazingly enough, it confirms our rational thinking about this. I'm rotating about z, so amazingly, it doesn't change z. and you get an alternate sign here, right? Plus in one, minus in the other direction. And if you realize before this, right, I had been with the same sign. So if one's pointing this way, the other one with alternating signs has to be 90 degrees off.
Right.
That's exactly what we would have expected it to do. So when you look at your answers, take 5 seconds to rationally check. So that's a reasonable look to them. So this has to be my Z0 cross PE. So I put that in, and I got R sine theta 1 minus R cosine theta 1 and 0. Oops, I got one more column to do. All right, the next one is prismatic or rotational? Prismatic. So for a prismatic joint, it's going to be Z1 now, the new axis, and 0. I'll do one of these for you. This is 0.
You're so kind.
Hey,
He is a caring,
I care.
care to choose the.
How about Z1? It's not like this one's a lot of work. I wrote on the board for you, okay?
Yeah.
You should realize at this point it's just a substitution. All the work's done.
Yeah.
All right? Once you have calculated those transforms, it was just substitution. I just remember I wrote up what Z1 was.
Yep.
So you just stick it in. There you go. Jacobian.
Quick question. For your determinant there, the notation you wrote for your final determinant was an I and then the actual magnitude. Is that only quaternion notation where you put the I ahead of time? And then if
Oh, you
it's
can put wherever
vectorial-
you want.
Oh, okay.
Realize this is a real number.
Yeah.
A real number commutes with an imaginary.
Right. Because like when you're just doing vectors, then you put the I hat at the end. In this case, there's no hat because it's quaternion.
No, they would stick the hat on this. It's
Oh,
not,
they still
when they
would.
stick the hat on it, it ain't a vector.
Oh,
It's a
okay.
quaternion they're treating, like, they call it a directional vector.
Yeah.
It's actually a quaternion,
Oh, okay.
okay? But notice, this is actually, they commute, okay? As it goes, it even commutes if you make it a vector, as it goes. So vectors always commute with a scalar.
Okay.
Okay, so it doesn't matter which order. So this now just comes down to personal preference, where do you put it? Now, I always put the direction first. And the reason is, yeah, it's easier to group. When I look at it, I mean, I was raised in America where we read left to right. Honestly, if I had been raised in a country that was right to left, I'd put it on the right. Because wherever you're going to see it first. Because of these two things, which matters more to you?
Direction.
Right.
The direction first, that's what you're going to group them on. So I just want to see the thing I'm grouping on first. So is it wrong the other way? No, it's just slower. So I just do this because it's a hell of a lot easier to pick out the directions. So, but yeah, I mean, you can flip them. I mean, you can be slow if you want. It's more work. I mean, but honestly, if you are from a country that goes right to left, it might actually be faster for you on the other side because you will naturally scan the other direction. That's perfectly fine with me, right? It doesn't change the math. Make it easy for you. You're the one doing the work, right? So whichever way you naturally read, put it that way. Commutativity is lovely. Do we feel comfortable how we could do this? We could add, I mean, you could add as many more of these stupid things as you wanted, right?
Yeah.
Where did you get Z1 again?
Where did I get which?
Z1?
So remember when we did the UT1, which was right here? That was going on? So remember, this is your X1, Y1, Z1. Boom. You just grab Z1.
Can you tell me again why in the first determinant element, why that became positive?
Because when you expand a determinant, right, that goes on, right, so to go from a third dimensional one, you take the cofactor, so you go I times its cofactor. Its cofactor is you remove this, and you remove this, and you take the determinant of the cofactor. That's the first one. So you'll notice it's I times this. When I go to the next one, when you walk down, the danger of writing these pens on my actual numbers, right? When I do J, right, this is 1, minus 1, 1. So this one is going to be minus J, right, because I stepped one down. And then you remove those, and you're left with the cofactor formed by this, which was 0, minus R1 co, right? And then 1, 0, 1, 0.
Okay,
Okay?
okay,
That makes sense?
yeah.
And the reason why you get this, technically you're kind of flipping these two as it's going to get them in order, and one flip inside the determinant causes a sign change. So to actually connect this side with that side took a single flip, which is a single sign change.
I was gonna say, if you look at, when you construct the determinants, if you treat it like a cylinder and actually
As you
it's
rotate.
cyclical, then
Yeah.
you just,
It's a cycle of one. If you do 2, you get 2 negatives. Right? Negative times negative, which gives you positive. That's why if you go 2 around, it's positive again.
Right.
So an odd number of rotations gives you a negative because it's minus 1 to the number of rotations.
Oh,
So this is minus 1 to the 0. You didn't have to rotate at all. Minus 1 to the 1. Minus 1 to the 2. So that's why the sign is out front. That make sense? Remember, the cyclical comes from, remember I showed to you inside of quaternions, there is that cyclic rotation that goes in? That's why there's a cyclic rotation here. And for the same exact reason, you're rotating the dimensions.
so when you dropped it down from there,
So all they did is I just then copied it in and I got the minus. When you go to the last one, the K, you take the K times and you remove this and that and you're left with this. The determinant of that component, which is what I wrote here.
I got that, the bottom line there.
So it's
IR,
this
yeah.
times this
Okay.
minus this times this.
Okay, so that's,
Right.
it's the minus.
So
oh.
it's 0 times 0 minus
Ah,
that
yeah,
times
that's
that.
right. Okay.
minus.
0 times 0 minus this times
that
this.
times that.
0 times this minus this times this, which gives me 0. So you just keep breaking them down until you get 2 by 2s, and then you just follow the cross. Good? All right, how much time do I have?
Negative 10 minutes.
Because this is so much fun. All right, so we feel good about getting Jacobians now at least?
Yeah.
Okay, I want to really quick next time just do a little bit of differential motions and then plug right into the ground. Okay.
Actually,
Yeah.